Hello everyone, I'm Yu-Ming Chen, a PhD student from the Grass Lab at the University of Pennsylvania. I'm going to talk about optimal reduced order modeling in the context of bipedal locomotion. This is a robot named Cassie in the simulation. Let's ask the robot to do one simple task, walking downhill at a constant speed. Currently, there are many existing methods that could achieve this. One way is to use an optimal control approach called trajectory optimization. In the optimization, we use a forwarder model which can describe the motion of the links of the robot, so this approach could leverage our full knowledge about the robot and generate an optimal trajectory for each joint. However, this method could take up to a minute to plan for just a single footstep. Therefore, some people use simple models such as linear inverted pendulum. They assume that the robot is a point mass, plan a trajectory from this, and then ask the robot to track it with its center of mass. They also plan the footsteps at the same time, then ask the robot to track it with its swing foot. And because of the model's simplicity, these methods can plan desired trajectory in milliseconds. Another popular model is called spring-loaded inverted pendulum, where we replace the legs with a spring. Similarly, we plan trajectories and ask the robot to track them. Since we're asking a complex robot to behave like a very simple system, we automatically lose performance. Therefore, many people have attempted to extend the model to try to add the performance back in. For example, some people add an actuator between the mass and the spring. This model is called A-slip. Some add moment of inertia to the body. Some use two springs for the legs. Overall, we can see that these model extensions require human intuition. Therefore, a goal of these projects is to find the best reduced order model. What do I mean by the best? It depends on which metric we pick. Some people might want to minimize motor torques, and others might want to minimize energy consumption. So the best model here is the model that could allow the robot to finish the task with a minimum cost. The task could be walking at different speeds, walking downstairs, or walking with different stride lengths. Since we want the robot to be good at all kinds of tasks at the same time, we take the expected value of the cost function over the task distribution. Also note that the reduced order model is a constraint on the robot, because we're asking the robot to behave like a low-dimensional system. Therefore, we will expect that the cost goes up when we embed the reduced order model into a robot. So the goal here is to look for the most permissive or the least restrictive model. Now let's talk about what is reduced order model. So given a full model, we want to find the reduced order model. Here I take the 5-link planar robot as an example for the full model. The plot on top here shows the generalized position of the robot when it's doing some tasks such as walking. And the bottom plot here shows the same thing but for the reduced system. We know that there exists a mapping from the forward model position to the reduced order model position. And the reduced order model can have its own dynamics. So we define our reduced order model by these two functions, the mapping and the dynamics. Just a quick note, looking for the optimal functions R and G is an infinite dimensional problem. So we parameterize these two functions with the set of basis function. This is a common approach used by the community. So now the problem becomes finding the optimal parameters that minimize the cost of the robot. Since we are optimizing the expected value, we naturally pick the stochastic gradient descent algorithm to solve this problem. Here I briefly outline the algorithm. First, we initialize the model. It could be any model, you can pick your favorite. Then we randomly choose a number of tasks, and for each task, we evaluate the cost. And then we calculate the cost gradient, and finally take a gradient descent step. We repeat these steps until the model converges. So one detail about how we evaluate cost. We run trajectory optimization of the full model and use the optimal cost as the cost for this task. In the trajectory optimization problem, H and G are the cost and the constraint for the full model, and the subscript task here means they're task dependent. And the constraints in the bottom two rows are the mapping and the dynamics of the reduced order model. So this is how the model enters as a constraint. Here is one result of the trajectory optimization. The video shows an optimal gait of the robot given a task. The task here is to walk at a certain speed and on certain ground slope. Since we asked the robot to act like a linear inverted pendulum, we can see that the velocity of the signal mass height stay at constant. And this is the gait with a different task. As for the gradient calculation step, we won't present here due to time limit. Please see the details in the paper if you're interested. So after a few iterations, this is the result. The plot here shows the cost of each iteration. It is normalized by the cost of the full model without any reduced order model embedding. And the video shows a few gates from the final iteration. From the result, we can see that although the model remains low dimensional, the performance is much better than the LIPs. Here is another example of model optimization. The tasks include various walking speed, ground inclines, and turning rates. And we choose to initialize the model with a 2D linear inverted pendulum again. We can notice that the initial cost is not high. The reason is that the model we use is not very restrictive Cassie and for this specific task. So the video here shows the gates from final iterations. Just to recap, we generated optimal models given full models and sets of tests. Unlike traditional approaches, the models do not easily map back to physically interpretable systems, but by optimizing, we can find reduced order models which better represent high performance motion of the original physical system. Now that we have the optimized models, we can do planning and tracking on the robot. We were able to do real-time planning, just like people already do with the existing models. Here is one example of planning the reduced order model space. So given a start and an impulse of the robot, we can plan the low dimensional space for the states and the input. And then we can ask our robot to track the trajectory y of t. But this is not the whole story. The truth is that the optimized reduced order models currently do not capture the impact dynamics of the robot, so we need to add the robot states into the optimization. The pre-impact state and the post-impact state. And we also need to add the impact map in order to stitch the low dimensional trajectories together. Here is the result of the planned trajectory. The task is to walk for 4 meters in 8 strides, and we ran inverse kinematics to visualize the gates of the full model. In summary, we provided the definition of our reduced order model, and we were able to find the optimal model automatically. We also presented a result for planning reduced order model space. As a part of the ongoing work, we're currently expanding the task space and optimizing different models. Later, we also want to evaluate the model performance on the real robot. And in general, there is no guarantee that the planned trajectory is feasible for the robot, so we could try to tackle this problem in the future. Last but not least, we hope that we could extend the model to capture the impact event and the impact dynamics of the robot. Thank you.